All right, everybody, thanks for tuning in. We're going to talk a little bit about the mean value theorem, sometimes referred to as the MVT for short. And just to go into a little bit of the details, draw a picture, and then we'll do an example. So it's an if-then statement, and remember the if part is sometimes referred to as the hypothesis. And try to spell hypothesis. You know what I mean, and the then part is the conclusion. So it says if you have a differentiable function for all x in the open interval, remember open, the endpoints aren't included, closed, the endpoints are included. If it's differentiable inside the interval, a to b, a continuous, everywhere, including the endpoints. The reason for that distinction is just for the cusps. You could have cusps at the endpoints, because remember, cusps are continuous but not differentiable. And it says if these criteria are met, then there's at least one number, there could be more than one, at least one number, in the interval where the derivative at that value is equal to the slope between the endpoints. So this is a mouthful, and it's easier to describe with a graph. So if you have some function, which we'll call f, and we define it on an interval a to b. This is continuous at every single point. And right at the endpoints here, this we could call f of a. This we could call up here f of b. It's continuous and differentiable at the endpoints. What this piece is saying is you could have cusps at the endpoints and it would still work, but this one is behaving very nicely. So here's what it says. This part right here says that if we look at the slope between b and a, that's the slope formula, and the slope would be the slope of this purple line. It says that there's at least one c value in a and b. So if we find some c value, we're going to show you how to find that. If we find a c value somewhere in here, this value would be f of c. But this theorem, the MVT, involves the derivative. And it's saying the derivative at c, which again is the slope of the tangent line, it's saying that that slope of at c, right, is equal to the slope, what is this saying in English? The slope between a and b. Why is it called the mean value theorem? Think of the mean as an average, and this is kind of this is the average between the endpoints. And we're saying that there's some value in the interval that's actually equal to that average. So that's where that term mean or mean value theorem comes from. This c value is the mean value. All right, so what a glorious mess. Let's see it in action to see if it makes a little bit more sense. All right, will the conditions of the mean value theorem be met? So that's like the if part. For the function x cubed minus 2x minus 1 on the interval 0 to 2. So just a couple logistics things. This is like our a value and our b value in some interval. And this is a polynomial and it's a cubic. Anytime you have a cubic, it's some version of this graph, but we're not going to have any issues with cusps or differentiability. And so I think that all of the if criteria are going to be met. And what this is saying is if these two things are met, then there should be some c value that we can find that's equal to the slope between the endpoints. And so I left off part of this, but the follow-up question is, find the c that satisfies the MVT. That's one of the classic questions. So the conditions are met because everything's differentiable and continuous. And so let's go through the algebraic process of actually finding C. So I'm actually going to draw just a quick pick, just so we can see what we're doing. So here's, x and y, f of x. And I'll use a couple shortcuts here, but we know that the y-intercept's -1. And all I really care about is the interval from 0 to 2. And so I'm for sure going to find some of these values. So this is 1 and this is 2. If I substitute, 1 in and try to find f of 1, I get 1 minus 2 minus 1. That's going to be down here at -2. And then if I find f of 2, I've got 8, right? 2 cubed minus 4 minus 1. We know f of 0 was -1. So you got 8 minus 4 minus 1. It looks like that's, 3. So at 2, we're going to be up at 3. So we can't see it very well, but if you verify it or fill in a few more pieces, I believe the curve is going to look something like this. It's going to come up, come down, and it'll kind of back up. So it has that cubic shape. And so just to remind you of what we're trying to find, if we're looking at the interval from 0 to 2, the MVT, you write it out again, says that there is some slope that exists between A and B. And there is some value, C, where C is somewhere between A and B, where the slope at that value is equal to it. And so I'm going to draw a picture and show you where the solution is, and we'll actually find the number. So if we're looking at the slope created between 0 and 2, this is kind of the average rate of change, right? The slope is the average rate of change. Somewhere in this interval, there is a parallel line. And it looks like it's got to be, these numbers, if you look at my cursor to the right, it's got to be somewhere in here. There's some line in there that's going to be parallel. Again, this picture's not perfect. I just drew it by hand, but the idea is, there's some C value in the interval. It looks like it's going to be between 1 and 2, where this MVT will be met. So here's the work that goes along with it. F of B would be f of 2 minus f of 0 over 2 minus 0. And I got some of this work already done for me. So I've got 3 minus 1. And on the bottom, I've got 2. So I've really got 4 over 2. That's a nice, convenient number. Should have done it in purple, but that's telling me that the slope of the purple line is 2. And so now if we kind of continue this idea, sure I'm good on time, we're saying that the derivative is equal to 2 somewhere. I'm saying that somewhere is at this C value. So I can find the derivative of that cubic pretty quickly. The derivative is 3x squared minus 2. Just use the power rule. And I want to know where that derivative is equal to 2. And so if I actually solve this, I'm going to have 3x squared equals 4. X squared equals 4/3. And then if I take the square root of both sides, I'm going to have this. And you could write this a few different ways. You could write it as 2 over the square root of 3. If I punch it into my calculator, I got 1.154. So we get 2 answers, and that's because if you look at the graph, there's another spot where there'd be a parallel line. It'd be over here somewhere. But we only care about the one that's on the interval 0 to 2. And that C value is, it looks like 1.154. I wrote it wrong. C is equal to 1.154. And C is just saying that it's a specific X value. And it looks like that matches up on my graph. And so that is the C value. That is the answer. That's the C value that matches up with the MVT. This other C value has the same slope, but it doesn't fall on the right interval. All right, we got a couple minutes just to kind of verify this if you're curious and tie it into an old concept. So what I got here is a Desmos graph, and that's what the cubic actually looks like. And in this box right here that's highlighted, I've got the slope, which was 2. And then here would be an equation for the green line that connects, f of b and f of a. I use the slope and then the point 0, 1. So if we want to check our work, check this out real quick. I could use the new point, which is y minus f of, and then that x value we found was 1.154 equals, and then the slope that we were making it happen was 2. It's a nice easy number. And then again, x minus x1, point slope, x minus the C value. If we do x minus that point that we found, oh baby, you can see the answer show up, and indeed it looks legit, it looks parallel, and that is the MVT in action. So, thanks for tuning in.